Okay, 8.4 vectors day one. Alright, some of the stuff we're going to talk about with vectors you guys will be very familiar with if you've been in physics. If not, that's okay. You're going to learn everything you need to know in this class. I won't assume that you know anything other than what I'm teaching you. And for some of you, though, what you've been doing in physics hasn't made a lot of sense to you, but it will after this lesson, at least in terms of the vector part. So it says a lot of quantities can be determined by their magnitude. Length, mass, area, temperature, energy are a few. This means that there's only one number, okay, and this is called a scalar quantity. So think about if someone were to ask you for the temperature, as long as you're knowing that you're in the same units, you just need one number. You don't need two different components or multiple components. Same thing with area. Area is 20 square kilometers. Again, you have your units, but that's not its individual component. That's just the understood units. So it says to describe displacement of an object, two numbers are required, a magnitude and a direction. Okay, so magnitude, this word may scare you, but you've been dealing with magnitude since you were in elementary school. You just didn't call it that. You just called it whatever it was for that particular problem. Velocity is a perfect example of this because you have to have a direction. And sometimes it's as simple as forwards or backwards, but usually it's, think about if you're driving in a car, you are going a direction, like a north, south, east, west, or, southwest, so many degrees. That's your direction, and that's as important as your speed if you were giving, trying to predict where a car would be after a certain amount of time. A scalar quantity doesn't have direction, so think about volume. Or if you were just talking about speed, that doesn't have direction, so that's the difference. So a vector can be thought of as a directed line segment. So let me draw a vector. It kind of looks more like a ray, the way we draw it, but that's just because we want to give it a direction. And so the notation for this looks like a V with kind of almost like a half arrow on top. That's just vector notation. It has a starting point, which is called the tail. Okay, this is the initial point. Now, a lot of times this is going to be the origin, but not always. So this is the initial point. Okay, it also has a head. The head and tail is just slang for initial point and terminal point. Terminal is just where it ends. Okay? Equal vectors. Well, equal vectors, they just have the same magnitude and direction. So there's vector A. Now I could draw vector B way over here, but it's going to be heading in the same direction and it's going to be the same length. Okay, this arrow doesn't mean it continues to go on forever in that direction. In this case, it just means that's the direction that it was going, not the other way around. And so C could be, really close. But again, these are all parallel lines and they are all heading in the same direction. They also have the same length. That's what makes them equal. So this is very important to simplify things down for us because vectors have this horizontal and vertical component to them. You can think of vectors in terms of magnitude and direction. You can also think of vectors in terms of its horizontal and vertical component. And so here we have an initial point at the origin, which makes things easier. And then the terminal point is just at the point AB. So think A is horizontal, B is vertical. And so it says to draw this vector. So really all we're going to do here is we're going to draw the point 0, 0, and we are going to draw the point negative 3, 4. We're going to connect them, and there's your vector right there. Okay, not that hard. So to find magnitude, now you actually have all the trig you need in order to answer this next question. This says the length of vector V, okay, or the magnitude, absolute value. Now, we used to think of absolute value as a distance, and it is distance, but it's more complicated than that. It's a distance from 0, and in this case, it's the distance to the origin. Now, if you think about this as a right triangle, okay, the base of this triangle is 3, and the height is 4. What then would be the hypotenuse? Well, we know it has to be 5. Okay, so the magnitude of this vector is 5. Now, in order to find it for this problem, find the magnitude of vector V, what we would do, or let's say it was not obvious what the magnitude is, we would square the horizontal component. Now, in this case, this truly is a negative 3, but squaring it it's okay if you left that off because you're going to get the same number in the end. So this is going to be 9 plus 16, which is 25. When you square root that, you get 5, which is what we predicted. Okay, and that's how you find the magnitude of a vector. Now, when you're finding direction, okay, this is talking about an angle, okay, and that is going to be our theta. So let's think about this. Okay, this is a right triangle. I didn't draw the right symbol very well, but this is a 90-degree angle right here. And from this theta, I know the opposite, and I know the adjacent. I also know the hypotenuse, but what was given to me, let's just go ahead and use that. So that's going to be tangent then of that theta is going to be equal to 4 over 3. And again, I'm not going to even put the negative here because doing so will cause confusion in the next step. So then you're going to take arctan of 4/3. Now this is actually not my full angle, but this is going to give me my reference angle, which is 53. You type this in, you get 53.130 degrees. Now that's just the reference angle. When you're finding this angle, you really are wanting to start at 0 degrees, just like how we did the whole semester in trig. Okay, so what do we need to do with this number? We need to, in this case, subtract it from 180. Now, if this landed you in other quadrants, you might do something differently. But in this particular case, we know what to do. And so this is the direction of that vector. So we've got horizontal, vertical components. We've also got magnitude and direction given an angle. Okay, and all related to the trig that we've been doing this semester. It says if a vector v is represented in a plane with an initial point and a terminal point, then the component form, and when you see component form here, just think of the most simplest one where it starts with the origin. This is a way of taking when it doesn't start at the origin and making it start at the origin, which will always make it easier for you. You're just going to subtract the two x values to get a new, simpler x value, subtract the two y values. Now I'm going to show you kind of why this works on this next example. So this says find the component form of vector u with initial point -2, 5. So I'm going to plot this right here. And terminal point 3, 7. Okay, so this is my vector right here. This is my vector u. If I were to go ahead and do what they told me to do on the last page, I would just subtract. I'd go vector u is 3 minus -2, comma, 7 minus 5. Whoops, not a parenthesis there, but vector. This would give you 5 and 2. Okay, that is the component form. Now let's plot this starting at the origin and using the component form and see what happens. Notice that these two vectors are parallel. They're the same length. That's because they're equal vectors, except that the new u is going to be much easier to work with than the old u if I wanted to do things with it like magnitude or angles or any of that. Okay, let's look at the next part. Vector v, 3, 7. Okay, so it's sketched with an initial point of 2, 4. Okay, what is its terminal point? Now 3, 7 tells me it's going to go to the right 3, it's going to go up 7. Now I'm off the grid at this point, but that is my vector v. Now you can either add 3 and add 7 to this. That would probably be the easiest thing. You could actually use the formula, but let's go for easy. What would be the terminal point? Okay, if I added 3, that would give me 5. And if I added 7, that would give you 11. This is, and I'm putting this in parentheses because it's a point. This is the terminal point. Okay. Let's look at part C. Part C says sketch the representations of vector W, and then they're going to give us 3 different starting points. Now, I want you to predict I'm going to draw 3 different vectors. What do you predict will be similar to all 3 and different to all 3? Okay, let's see if your prediction checks out. So if I start at 0, 0, which is the true component form, right 2, up 3, okay, that is the vector W. And an equal vector would be if I started somewhere else, but I'm still doing the same thing, meaning right 2, up 3. Now so far I've got 2 vector W's, and they're parallel and they're the same length. Let's see if this happens on the third one. Right 2, up 3. And there you go. All three W vectors, although they're in different placements, they go the same direction, they have the same length. That's magnitude and direction, that's what makes up a vector. There you go. Okay, let's look at D. D is going back to U, this vector U, and it's asking us to find the magnitude of twice U. Well, first we need to do twice U. Okay, twice U will be twice the horizontal component and twice the vertical component. So now I have a new vector that's twice as long. Okay, 10U, and let's find the magnitude of this. So this would be the square root again. This is how you always find magnitude. 10 squared plus 4 squared. So that's going to be 100 plus 16, that's 116. And if you simplify this radical down, you get 2 root 29, which is something you would need to do. And there you go. Okay, I'm going to do something very similar on E. I'm given this new vector A, and I am considering also my vector U. Let me rewrite this one down. This is 5, 2. And the first thing I'm going to do is add vector A to vector U. So I would add the horizontal components. That's going to give me 6. I would add the vertical components. It's going to give me -1. And I wrote something here I shouldn't have. I should not have put these here. Because what I've done here is just added vector A plus vector U to get a new vector. Now if I want to take the magnitude of vector A plus vector U, I got to take the magnitude of my new vector. So it's going to be square root 6 squared plus -1 squared. So 6 squared is 36, plus 1 is 37. So that's square root of 37, which does not simplify. Okay, so there's a lot of different things you could do from here. Okay, if you look at the next part, it kind of sums up what I did and leads us into the next thing. It says the sum of two vectors. If two vectors are placed head to tail, the sum of is the net displacement from the tail of the first vector to the head of the second vector. So let me draw a picture so that this is not so confusing. So let's say here you had vector x, and then from the head of this vector and a tail to another vector, here you had vector y. Different magnitude, different direction. I guess they could be the same, but we'll just say in general they're going to be different. Then the resultant vector, which is what this is kind of leading us to, is this net displacement, the total displacement from the tail of the first vector to the head of the second vector. This is called the resultant vector. Okay, and this is going to be vector x plus vector y. All right, now notice that this is not a right triangle, so we might have to bring in some law of sines, law of cosine stuff. Okay, now let's talk about this in the problem we just had. Okay, so first we had vector A, which was starting at 0, 0 and ending at 1, 3. Okay, so here's vector A. Next we had vector U, which was 5, 2. So we'd go 1, 2, 3, 4, 5, and then up 2. This is how you'd add vector U. And let me use a different color here. This net displacement here, okay, would be vector A plus vector U. Now if you remember, I mean for you guys it's just a little bit ahead, this was 6, -1, which is what's clearly shown right here, 6, -1. Okay, and we know the magnitude of that is 37. Now, on this next part, it's talking about subtraction. Okay, and subtraction is very close to adding all the time anyway. It's just that, you know, the only thing that's changing is we have opposite directions. So let me just draw a simple example. So here's vector v. Well, negative vector v would be parallel. It'd be almost the same, except to have an opposite direction. So let's talk about what would be vector A minus vector U. Well, instead of going right 5 up 2, I would be going left 5 down 2. So a completely opposite direction. So it'd be like adding a negative vector. And then this right here would be vector A minus vector U. Okay? So let's use this in going into the next example, which says if we're given the magnitude of vector A and the magnitude of vector B and the angle when they're placed tail to tail is 53, then let's find some information. Basically find the magnitude of the resultant vector and the angle. Okay, so here's vector A. We'll just call this vector A. And it says tail to tail gives me an angle of 53 degrees. And that does not look like a 3. I'll clear that up a little bit. Here we go. Now this is nice, but in order to even use resultant vectors or add vectors, I don't want tail to tail. One of these has got to move so that it's head to tail. Now the easier thing to do here would be to move B so that instead of its tail is at A's tail, is to move B to be up here. Now keep in mind, it has got to be an equal vector, meaning it's got to be parallel, it's got to be the same length. But when I do this, okay, and I connect them to make my resultant vector, this 53 degrees is shattered. It's not cut in half, okay? That would happen if this were a square, but it wouldn't happen on all quadrilaterals. So we've got to use good knowledge. Now this is a parallelogram. It may in a specific instance be a rectangle or something else, but we know for sure it's got to be parallelogram because these B's are parallel. So think about consecutive angles on a parallelogram. This angle up here has to be supplementary to 53. So that angle has to be 127 degrees. Okay, and now just to make this a little bit easier, let me redraw this into just a standard triangle without all the arrows and everything. And I'm going to go ahead and just put R for resultant vector, and I'm going to go ahead and put in the numbers for A and B. All right, now this really looks like something we've already been seeing last week, which was the law of cosines problem. So setting up law of cosines to find R, and when I find this R, this will be the magnitude. So R squared will equal 5 squared plus 9 squared minus 2 times 5 times 9 cosine of 127 degrees. Now, I'm not going to work all this out. You can do this on your calculator. You've already been practicing this, and this gives you 12.656, which is the magnitude of the resultant vector. All right, now they also ask you to find the angle. They're very specific about the angle. They want the angle the resultant vector makes with A. So they're asking for this angle right here, or in our triangle, they're asking for this angle. Now you have a couple different options here. If you use law of cosines, which I think most of you would, you need to set it up as 9 squared equals 5 squared plus R squared, and R here now we know is 12.656 squared minus 2 times 5 times 12.656 cosine of theta, and then you need to solve for theta. Now it will make this, you know, more accurate if you don't round, and your theta here is going to be 34.6 degrees. Now I've rounded to the nearest tenth here, okay? And so that kind of saves you from having to worry too much about rounding and everything. As long as you're rounding to 3 decimal places, you should definitely be accurate to the nearest tenth. Okay, let's look at number 5. Number 5 is a little bit different. Okay, first of all, on number 5, they're not asking us for the direction, they're giving us this direction. So when I draw it, you know, you always start at 0 degrees here. 143 degrees puts you in the second quadrant. Okay, so here's your vector A, and we know it has a magnitude of 3. Now, if it wants to break it down into horizontal and vertical, the easiest thing for you to do would be to make this into a right triangle. Now, we know 143 degrees is important, but that's this angle. Okay, what would really help me in this triangle is to know this reference angle. So you're going to have to do 180 minus 143. So it's going to give you 37 degrees. Now, remember that A and B are representative of, A is my horizontal component, B is my vertical component. So just use good trig. And I'm talking the first week of school trig. So this is going to be, adjacent over hypotenuse. So it's going to be cosine. So cosine of 37 degrees is going to be equal to A over 3. You would multiply both sides by 3. And so A would equal this magnitude times cosine of the theta. Type that into your calculator, and that would give you negative 2.396. And hopefully it makes sense that your horizontal component is negative. All right, now for your other one, you're going to use sine, because it's going to be opposite over hypotenuse. And so the B value is going to be 3 times sine of 37 degrees. And that's going to give you 1.806. That makes sense that that's positive. So if we're resolving A into its components, okay, this is going to be negative 2.396, comma 1.806, and we put it in vector notation. Okay, next up is kind of a box that tells you and sums up what we just did. And here they have it in the adding it up, but off to the side here, I would like for you to put, the magnitude of V cosine theta. This is going to give you your horizontal component. And then the magnitude of V times sine of theta. This is going to give you your vertical component. And here theta is your reference angle. Okay? So when you're looking at number 6 and you're given two different vectors, both their magnitude and direction, and you're trying to find the resultant vector, well, first thing is we need to figure out what is true about vector A and vector B, okay, before we add them. So vector A, I know, is going to be 5 cosine of 70 degrees. Okay, and the vertical component would be 5 sine of 70 degrees. Okay, likewise for B, we're going to have 6 cosine 25 degrees, and then 6 sine 25 degrees. Okay, from here it's calculator work. Okay, you can pause the video and plug all these things into the calculator. You need to be comfortable with them. 1.71 and 4.698. For your vector B, you're going to have 5.44 and 2.535. Okay, all of that to get to part A, which is find the resultant vector. Now remember, the resultant vector is going to be vector A plus vector B. Now you didn't have to actually figure this out into decimals in order to do this problem. What we could have done is just typed in 5 cosine 70 plus 6 cosine 25 to get that new horizontal component. And again, you could have just added these two, or you could add these two decimals, and that would give you your vertical component. Now notice that both of these are positive. This is going to put us in quadrant 1, and that's not so important for the magnitude, but it will be for the direction. Okay, so if we're trying to find the magnitude of vector R, this is the magnitude of vector A plus vector B, which is going to be the square root and the sum of these squares of these two numbers. Now, it's to your benefit not to round as you go. Now, when we're writing this down, we have no choice but to write down the numbers. But when you're using your calculator, it's good to not have, get rid of as much rounding error as possible. Okay, and this is going to give you 10.170. Okay, that's your magnitude, rounded to 3 decimal places. It's also asking for direction. Okay, so if we think about the direction, I already said we were in the first quadrant, which you knew we had to be in because both the horizontal and vertical components are positive. So we already found, this 10.170, that was the hypotenuse. Okay, what we're finding now is this theta. Okay, and it's nice because we're in quadrant 1. We don't have to worry about subtracting from 180 or any of that business. You're typically always going to use tangent here. There are ways around it, but that's the convention. And so the opposite, the vertical component, 7.234 divided by 7.148, and that is going to give you your 45.343 degrees. Now again, you don't have to worry about putting this in a different quadrant in this problem, but you could in another problem. Okay, please bring your questions to class.